Alright then, so here's a problem. Calculate the overall enthalpy change of this reaction. That's just another way of saying the overall energy change of this reaction. Alright, so perhaps the place to start here is to draw the molecules involved in this reaction. I'm just going to make a little correction here because the eagle-eyed of you will have noticed that this should be a little 4, this should be a little 2, that should be a little 2, and that should be a little 2. Alright, I'll just perhaps rewrite those CH4, 2O2, CO2, and 2H2O. So let me very quickly draw out those molecules. Now very often they'll be drawn for you, or by the time you come to sit your exam you'll be able to draw these for yourself. But let me do that for you for today. So CH4 looks like this. Remember, this is important to be able to see these molecules because you need to be able to count the bonds. There's 2O2, CO2 looks like this, and we've got 2 water molecules, O, H, and here's the second one. Okay. All right, so let's calculate the amount of energy, the energy change, the enthalpy, the overall enthalpy change, the overall energy change for this particular reaction. So here's what we do. We're going to draw ourselves a table, and there's going to be two halves of the table. On the left-hand side, and you do this in your exam, actually go to the trouble of drawing a little table. So on the left-hand side, bonds broken. In other words, the reactants. And on the right-hand side of the table, bonds formed. Okay, or in other words, the products. And just draw that line down the middle there. Alright then, so let's start off with calculating the amount of energy needed to break the bonds of the reactants. So we need to count how many of each type of bond there are. Let's start with the CH4 molecule. Well, if we count them, there are 1, 2, 3, 4 CH bonds. So 4 times CH bonds. And so the energy required to break those are 4 times, and then when we look over here, we can see that each CH bond needs 413 kilojoules per mole to break. 4 times 413 kilojoules of energy. And if you get your calculator out, you can see, you would work out that that comes to 1,652 kilojoules per mole. What other bonds do we need to break? Well, we need to put energy in order to break these bonds here between the oxygen atoms. So we've got 2 of those, so it's 2 times, now what bond is it? It's this one here, isn't it? Okay, that's 2 times 2 of those bonds, so that's 2 times 498. And smash that into calculator, that comes out as 996 kilojoules of energy in order to break those bonds. Now if you add 1,652 to 996, that gives you a total of 2,648 kilojoules per mole of energy needed to break all of those bonds. Good so far. Now we need to calculate how much energy is released when we make the new bonds of the products. So again, we're counting the numbers of each type of bond. So let's start off with the bonds between the carbon and the oxygen. So we've got these bonds here. So that's 1, 2, so 2 times carbon-oxygen double bonds. In other words, 2 times 736. And 2 times 736 is, of course, 1,472. 1,472 kilojoules per mole. Okay, and what other bonds are going to be made? Well, we've got 1, 2, 3, 4 times hydrogen-oxygen bonds. So how much energy is going to be released when we make 4 hydrogen-oxygen bonds? Well, hydrogen-oxygen, there's 464 joules of energy in each of those bonds. So the total there is 1,856 kilojoules per mole. So once again, we add up that and that. So the total amount of energy released is 3,328 kilojoules per mole. And then we use our equation. The overall energy change is equal to the energy needed to break the bonds, which was 2,600, bear with me, 2,648 minus the amount of energy released when we make the new bonds of the products, 3,328. And you smack that into your calculator, and of course that comes out as minus 680 kilojoules per mole. That's the answer. The overall enthalpy change of this reaction is minus 680 kilojoules per mole. And remember, this minus number tells you that this is an exothermic reaction, which you would expect because this is the combustion of CH4, which is methane. And you know that any combustion reaction, burning, is going to be an exothermic reaction because, of course, it's going to give off heat. So remember, that negative number is what tells you it's exothermic. If it turned out to be a positive number, what would it be? Yes, that's right, it would be endothermic. Good.